Yeah, so my name is Jared Lee. I am from Cadence Design Systems. I am an application engineering director. I've been in the industry for over 25 years. I spent my first 10 years at Intel. Intel, I did over 30 plus designs. And in 10 years at Intel, that is a lot of designs, trust me. I worked on everything from their ASIC controllers to flash to CPU designs. And at 10 years, I had my sabbatical extended 3 times. And I went on my sabbatical, got an interview with Cadence, and never went back. That's literally the truth. I have worked for Cadence now for 15 years. You might have heard of all the remote work that they've been talking about for over COVID and how people have been working remotely. I have been doing that job for 15 years. So it's like, okay. Only downside is I didn't get to see as many customers during that time. So the good news is we're back out seeing customers again and visiting with them. It's good to see old friends and faces and see new ones. So if you're looking for a remote work job as well, Cadence is a place to come. So, okay, so we're here to talk about the Cadence digital implementation and sign-off. There are some marketing slides in here. I apologize. That's required because we're doing a presentation. But I will spend most of my time talking about three areas. I will talk about our high-level synthesis solution called Stratus. This is where we take System C to C++ and take it to RTL. I will spend time talking about our Genus RTL synthesis solution. And then I will spend time talking about Innovus, our place and route and floor planning solution that we have. Okay, this is interactive. Feel free to ask questions. If it's too much, I'll table stuff and we'll answer it probably afterwards, or we'll take more questions later. Go ahead. Okay, so why Cadence? Cadence is 19 of the 20 top 20 semis use Innovus, 16 use Genus, 15 use Tempest. All of them use Conformal. All of the products are in the product areas that I actually currently work in. There's very few companies out there that doesn't have some Cadence tool in it. So there's not a device in this room that Cadence tools did not touch, especially in terms of semiconductors. This was actually from last year, so a lot of us focused on 5 nanometer. We've done 3 nanometer tape outs since then. I've been on a few of them actually. But this is currently where we're at. This is talking about what is our full flow advantage. We're talking about the ARM Neoverse and the fact that there are now in the automated solutions, we're hitting 4 gigahertz, which would have been unheard of a few years ago, that automated solutions could touch 4 gigahertz and do a good optimization. Part of that has to do with the fact that devices now take 1 or 2 picoseconds. So that makes a big difference too. So at Cadence, one of the things we try to do is we work on these core engines. We try to take the sign-off engine, the engine you're going to go tape the design out with. So for example, the sign-off static timing analysis solution, the sign-off power analysis solution, at least the sign-off level of DRC, and integrate those directly through our whole solution from actually all the way up from HLS all the way down. So we do a lot of that level of integration that does differentiate us in the marketplace. I know that our competitors have been trying to play catch up in this space for a long time. This has been part of our DNA for my entire career at Cadence. We always take those sign-off level engines and integrate them everywhere. If we need to, sometimes we got to tune them down a little bit. They can't run, the sign-off quality at the highest levels, but we do have that ability to draw on that experience. A good case in point, for the DRC, for example, when they implemented the first double patterning processes or FinFET processes out there, Cadence chose to take an approach of what we call coloring. We actually said, we're going to color this mask one set, and color that mask another set, and then we have the 2 different DRC rules. Made it a lot easier for the tools to handle it, and put us ahead of all of our competitors by 10 years. When they came down to triple patterning and quadruple patterning, the competitors go, oops, we got to catch up. And that's exactly what happened. That's just an example. Okay, as of late, we also released our machine learning algorithm. It's called Cerebrus. This is the future of our designs. I think one of the things that you'll see in RTL to GDS2 is people take a design, they run it through, and they run it 50 times or 30 times to figure out the right recipe. Well, we've realized over time that is a giant waste of time for people. So we want machines to do that for us going forward. And so we introduced this capability to Cerebrus. It is what we call a force multiplier. So we've seen design companies that used to have 15 people go down to 5 people because they know how to use machine learning effectively. And some of that was because they just got hired away, but that's not, you know. Think about it this way too. Designs aren't getting, yes, the manufacturing is getting smaller, but the actual content of that design is not getting smaller. You know, all of the new algorithms you see when they actually put machine learning on your phone and AI on your phone, that takes more transistors, that takes more silicon. Okay? That means it's more complex, right? So you need to have the solutions to be able to handle that complexity, if you will, and be able to go into that. And Cerebrus is a good start to it. Today, it is working well with our RTL to GDS, and next year we will release it with our HLS solution as well. Same solution, same problem set. You have 200 microarchitectures you want to run. Which one gives me the best power, which area of performance? Let the machine learn that and figure that out. Don't figure it out by hand. I actually talked to. Go ahead.
Can you tell me what knobs in the RTL to GDS2? What's the most important knob that Cerebrus is tuning?
Oh, there's a lot of different knobs.
Yeah, I know. That's why I asked. I know there are. I mean, I've done these tools in industry, so I know there's a ton. But which ones are the most important ones?
Well, there's not one knob. I think right way to look at it is that in this particular, we do what's called a reinforcement machine learning. Okay, so we are setting weights and we set a target number based on those weights. And the weights that we target are usually power, performance, and area. So power in terms of total either leakage or dynamic or both. Right now, I think it's set to both automatically. Performance is usually in terms of WNS and TNS, worst negative slack, total negative slack. Okay. In Stratus, the TNS is performance is different. It's number of cycles of latency or throughput. Yeah. Okay. But here it's WNS, TNS. And then it's area. How much area do I consume? Now, of course, there's other things we can throw into the weights too. We can say, oh, well, hold time's really hard on this design, so we'll make it a priority. IR drops are a hard problem on this design. Make that a priority. So we can weight them however we want. And we use those scores to figure out, we'll kick off like 10 or 20 of different jobs. One will run the baseline and everything measures off that baseline. And then we can branch off of it, we can parallelize it. If the score goes the wrong direction halfway through the flow, we'll just kill it. So it's a very smart engine in how we actually operate with it. So when we released it, they called them primitives, is how you set up the scores. And we're changing it to apps. Why? Number one, because people understand apps better. But two, because we're making it more focused. So let's say I want a floor plan exploration, we have an app for that plugs into Cerebrus. So if there's more questions on it, I'm happy to answer it. At the Cadence website, you can actually find the design with Cadence. You're welcome to go watch these videos. I'm not going to go through them all right now, but there's an imagination GPU, machine learning for advanced nodes, and then this is another one from Renaissance. And there's many more going on. We have many more active evaluations. Companies are adopting this solution. It will take over. I doubt you'll see a company out there in the next year or two that is not investing in machine learning at some level, at least at the larger scale companies. So, okay, so this is looking at some of our difficult challenges that we have to deal with. As you continue to move down nodes, 3 nanometer advanced node, we have heterogeneous and 3D IC, and power and energy optimization. These are kind of the key focuses we've been putting in as of late. One of the things you see, like, for example, in 3 nanometer, so in standard cells, you're used to a single right row cell, right? Well, they decided to mix them so they can get to the smaller geometries. So you have double height, you have single heights, and the 2 different heights. And your tool has to be able to handle all of that and understand what are the placement complexities, how do I solve my placement algorithm to handle that. Anything below what we call double patterning. So everybody's used to resistance and capacitance, right? So temperature goes up, right? Capacitance goes up, correct? Everybody, all right, every second ahead, right? So temperature goes up, what happens to resistance? It goes down, right? Okay, so the issue we have is that these copper wires are really good at low resistivity, right? Really low resistance. But as you raise the temperature, the operation of the switches, right? The capacitance goes up. So we look at we used to look at everything, at least from a setup time closure point of view, in what we call RC max. And we look at it like 120, 125, right?
Worst case 10.
Yeah, worst case 10. That's how we look at it. What happened is when we went to FinFET and we went to double patterning, the wires got really thin and really small, which means they're highly resistive. So now we were thinking everything's at 125, but what they realized, if we look at where other chips operate, some operate at minus 40, for example, right? That became the bottleneck because resistance is dominant. So the concepts of things like multi-mode, multi-corner became very important at these process nodes because now you're looking at literally 2 different temperatures to close setup. Same thing for hold, but that's the truth. So when you look at in anything that's double patterning or 16 nanometer below, they're traditional, look at the worst corners in the low voltage, the slow process, and the high temperature doesn't hold anymore. You got to look at the first 2, process and voltage is the same, but the temperature, you have to look at the cold corner as well, because it's in reality, in that cold corner, you can actually have a lot of timing violators, right? Because the wires are very resistive. And as we continue to go down the metal stacks, as we continue to shrink down to triple patterning and with the self-aligned SACD, which is another one they use as well, those are continuing to get more resistive.
So hold times is going to be an extra challenge because there you worry about fast paths.
That's right.
So which temperature is the right temperature for hold?
We check them both. We check them all now. That's what we do
You got
now.
to check probably more than just both.
Yeah, it's opposite. So you're looking for RC min, and then you look at the high temperature and you look at the cold temperature because you got to look at both.
Yeah, or even in the middle, I'm guessing.
All right, because the high temperature, these are faster, right? At the cold temperature, these are faster. So, and paths can fluctuate between the 2. So it's really exploded to some degree. And if we ever get to, one person we should bring in here sometime, Doug, where is he at? We should bring Christian Ludemeyer out of Marvell over. He's a really good static timing analysis, spends a lot of time at Tau. And you can hear his argument about why we shouldn't be using 100 multi-corners. We should be using 1 and scaling the capacitance each direction. But it's a really good argument. 3D IC, as we continue to shrink process nodes, this is becoming more and more relevant. The most SoCs nowadays are using, or at least the high performance computing is all using 3D packaging. They're not using just a straight package. They're actually using a silicon interposer, or they're directly tying them through what we call through silicon vias. There's 2 different types of 3D as well. There's this, and then there's the, I'm forgetting the name for it, but it's where you can actually build multiple devices. And monolithic, thank you. Monolithic, you can build it on the backside. You can build another layer of silicon and build it up. That's all coming.
How many are you hard?
Yeah. Well, think about this monolithic. When you build transistors, for example, in monolithic, you could build your high density logic in, like, say, 2 nanometer or 18 angstrom, like what Intel's built in, right? Or you can build the backside, so you can build it in, say, 28 nanometer, right? And in that sense, you could have put all your clock drivers, put all, anything you need to drive long distances on that backside, and everything else that needs to have high density logic to be on the front side. So that's going to take, because that will require dual placement. It is something we're working on. This is not something we're actively releasing, but over time it will come. Okay, and last but not least, there's been a real focus on not just power consumption, but energy consumption. So just because something has at its peak power doesn't mean it's at a peak energy consumption, right? So for example, peak power was usually what you're concerned about for thermals. Where you're trying to look at how much, do I want to make sure my device doesn't degrade? Am I going to get thermal runaway? Those type of things, right? So how much heat can I handle without impacting my timing analysis, and can my package and my heat sinks and my cooling system handle that, right? But energy is more than that. Energy says, how long can I run my cell phone, right? How long can I run the AirTag? right? So energy, making sure we shorten up those energy cycles or manage the energy cycle is really important. So that's another piece we focused on heavily. Okay, so as I mentioned before, we spent a lot of time taking core engines that are sign-off quality and pushing them up in the design cycle and pushing them down in the design cycle. So for example, we want to take high-level optimizations and push them down into the right before sign-off. So I can do transformations at post-route, for example. I can do actual combinatorial transformations. And I want to be able to take things like, useful skew, clock skewing, and I want to push it up so I can do it at RTL synthesis. Both of those things we can do today, and we've been doing for a year or two now, actually. So those are for some examples. Leaps in productivity. I mentioned the biggest one I would put at the leap in productivity is HLS, by high-level synthesis by far. People can do 5 to 10x more designs in the same design frame you can do in RTL design, and that is the truth. We've seen it time and time again. I've worked with teams that weren't probably the sharpest guys out there, and they still saw a 2x productivity jump. They got twice as much done because they can run HLS. It's a big deal. Of course, the Cerebrus is mentioned here. We do have some RTL level floor planning stuff, but I think these would be my 2 points. Cerebrus and high-level synthesis are definitely the multipliers of force multipliers.
So typically there's a gap.
Okay, this is just talking about how we have integrated full flows. We were able to handle all the advanced process nodes. Of course, we can go all the way back up, right? And we continue to invest in that. This is something Cadence has to continuously invest in. And our customers require more and more productivity, not less. So we have to be able to handle block sizes of 5 to 10 million, which we do regularly now. This instance counts is what we call it talking about. And we have to be able to do it fast. People need, they want turnaround times, depending on what we're talking about. It's about 1 million instances per day for the full flow. So every million you add is another day. Okay, I pulled these slides forward actually this morning because I thought they were useful so you could see the whole flow. I don't know how many people are familiar with the entire flow. So we start at the high level. We can take on the design curation side, you can create it with HLS or you can create it with RTL. So HLS's biggest competitor is not other competitors, it's RTL. Okay? It's also part of the design creation is our Modus Design for Test. This is where you actually inject your test structures to make sure the design is going to work properly, that you have any speed paths. Can I actually correct the memories? That's like built-in self-test for memories, for example. Can I test it when it's actually in the field? So say it's a space-based application and you have 4 of them. Sure, it'd be nice to be able to test to make sure the part's still working if it has a problem. So they have lots called logic-based, for example. Conformal is our logical equivalency solution where we can say, hey, does this RTL and this implementation netlist match? It saves you tons of cycles of trying to figure out whether or not my gate level netlist matches my actual RTL. We have an ECO solution we built off of that as well. We can actually take the bug implementation, the bugs that you find in your design, and you can implement them back into the gate level netlist in a very short turnaround using conformal ECO. In the implementation side, we have the RTL synthesis solution called Genus. For power analysis, we have a tool called Joules. This is not just power analysis, but it's also power profiling and power optimization. If you want to do power profiling, Joules is one of the best on the market to handle that. We can put in emulation solutions. We can take our simulator output, put it right directly in, and you can sweep steps, windows, multiple simulations all at the same time. It's a very powerful solution. Innovus is our implementation solution. This is where we do floor planning, we do placement, we do routing, we do clock tree synthesis. This is where it goes out to actually, from out of the output of Innovus goes into sign-off solutions, where we're checking to make sure the final design for static timing analysis, for LVS, logic versus schematic, DRC design rule checking, DFM design for manufacturing, power sign-off IR drop, which is your current drop, your electromigration, and making sure all of the things sign off. The two other solutions mentioned here, Quantus, sign-off extraction, and Liberate are feeders into those sign-off solutions. So Liberate, we're building what we call Liberty standard static timing analysis models. Okay. Quantus is for our RC extraction, resistance and capacitance extraction. We use it both for cell level and transistor level.
I might just want to tell the students, so Liberate is Cadence's automatic way to do cell characterization that you guys probably did in one of your homework assignments in 477. And they'll automatically generate the SPICE files that drive the cell, extract the results, and put it into a format, the Liberty format that is the industry standard. For both timing, power, setup checks, fold checks, leakage, all of those things, it's very nicely automated. Of course, we don't let you use that tool because we want you to understand how it's done, but they got it nicely automated.
Yeah, no, we do. It's important that you have like I said, the foundations are important, especially as you come on, that you understand what the tools are putting out. This is kind of a run through again. It talks about some of the different things that I think that we differentiate on. I think I'll kind of walk through this already, so I'm not going to go back through it. For Innovus, I'm just going to build out the slide. I started before Innovus was a product, and it was a lot of little products. That's how it started out, and it's a combination of many. If you want to go through the history, I can, but if you think about it this way, floor planning was one solution, and placement was another, and optimization was another, and routing was another, and clock tree synthesis was another. The first integration of that was what we call the SoC encounter, or the encounter system. That has migrated to eventually the Innovus system that we have today. And the difference between tool A and Y, tool A, B, C, and X has been slowly modified between all of them, so there's less and less difference between them all. So for example, today, even Genus and Innovus and Joules are actually in the same, what we call business unit or R&D team, and that code's slowly merging now at this point too. Okay? And then last but not least, we talk about sign-off solutions. We talked about STA, we talked about Quantus, we said about what Voltus does. We mentioned Liberate, and the last one is the design for manufacturing. There's a lot of design for manufacturing rules out there. Some of those are based on actual design rules, and some are actually based on simulation models. And we have a simulator that goes off and looks at those simulation models and patterns to make sure we avoid those type of patterns to bring up yields. Right. One of the things we try to do at Cadence is when we do distribution, we don't hold on to a large memory model. We actually distribute the design and the computing. So you don't have to have one massive server, for example, holding the entire design, which would be problematic to run something at 1.6 billion. That'd be a lot of memory, right? Now remember what I said about 1.6 billion, right? So 1.6 billion, we can do that overnight, right? You can't, if you try to run that through one large server, it would not happen overnight, right? The way we're doing that is we're partitioning up both the design, all the parasitics and all that, and then sending it out to multiple servers and bringing it all back. And there's a master actually controlling the path between the two. So in DRC LBS, if you're familiar with what was called the Human Genome Project, they used a concept called stream processing, where they would package up a little job and send it out to go solve that problem on some other CPU, your home PC, or your PlayStation at home. So we use the same concept. We do DRC analysis now. We use stream processing. That allows us to scale up to upwards of 1,000 CPUs and every time you double the CPUs, you can cut the time in half. So one CPU is 1x, two CPUs is 2x, four CPUs is 3x, keeps going up. High-level synthesis. So let's talk about perception versus reality. So the perception was, or at least it was, as I've already walked into today, limited use at small companies with inexperienced designs, fair enough. The reality, 9 of the 10 top semis vendors employ Stratus, our HLS solution, in the design of billions of devices, and many of the devices you have now. It's a niche technology, limited impact, it can only do certain types of designs. It's kind of limited, right? We have found this to be business transformative. This is the use case here shown. A company used to take 3 years to develop their cycles, and the way they would do it for a 3-year project, this was a very large design, doing image processing, for example, is they would have 3 different design teams. And they changed it from 3 to 2, and they went from number 2 in the market to number 1. Now, I can't tell you who the customer is because we haven't got the endorsement to tell you yet. We're working on that. But it could definitely transform your market. Another local company, may not be aware of it, they actually have it. I don't have it. I don't think I have that one in here, but it's called Sentient. Sentient took a design. They had an idea, got a contract. I think they were an incubator out of Irvine. And the first day he had his architecture done, we turned the tools on, in the cloud, by the way. Had his architecture done. He tweaked it for about 3 to 4 weeks, right? And then he spent 2 months just trying to kind of squeak every ounce of power because he's trying to do a low power AI audio application, okay? At the same time that this company started, there was at least 2 other startups that we were aware of that were trying to do the same exact thing. So in the 2 months he had his architecture done. 2 months later he had it taped out. 6 months later he took over the market. And basically those other 2 startups had to shut down because they just beat the pants off of them in terms of being ready for the market, okay? Now part of that was they used a good analog part, but it was also because they were able to come up with a digital DSP running at, I think it was 50 hertz, is actually what they ran it at, right? Running extremely low power. So these are like audio applications that you can say, hey Siri or hi Alexa or whatever without draining hardly any power at all. So that's what the advantage that they came to market and dominated very fast. Okay, so from the time we turned it on, the time first tape out was 4 months. That's unheard of. That includes analog design and digital. All Cadence, all in the cloud. So he's another great lecturer if you want to bring him in sometime for HLS. He's local. I'm trying to remember, his name is Dave, I don't remember his last name right now, but he'd love to come by and say hi. Huh? Yeah, Dave Garrett.
I think I have Doug on speed dial.
Yeah. So if you want to talk, like I said, these are experts in Southern California, but Christian, I mentioned earlier, he's another expert customer that we work with. So
there's a perception that there's not a lot of hardware jobs in Southern California. I think it's changing.
Yeah. We have an office here. We had an office here. We closed it down because everybody works out at their house, but we have hundreds of employees in Southern California. I'm just one of hundreds. Remember that. Okay, hand-coded RTO is always better, is the perception, and the reality is we consistently deliver better power performance area within the required schedule versus hand-coded design. Now, schedule is the key here, right? If you have infinite time, right? If I have 2 years to develop a design, I'm sure you could beat my HLS tool, no problem. If you have 6 weeks, I will beat the crap out of you, and that's the truth. Because I can look at, the number of microarchitectures I can look at within the same period of time is huge. You can maybe look at 1 to 2, depending how big the design is. I can look at hundreds. And that's what makes the difference. We had a really good example of this recently with an eval we did with a company local here. They wanted to expand their video processing. And they said, okay, we'll give you a shot. We're going to have 2 RTO designers develop the same exact design, and I'm going to have the other guy build it in HLS. The other guy had it done within 3 weeks before the guys even started. They changed the spec. He had it changed in a week. They still hadn't started the RTL, and they realized, well, this meets our power performance and area. Why are we bothering to even compete against that? Move on. So they moved the 2 RTL designers off to another design. Only applicable to data path applications. I've talked about a lot of them from that perspective. But we're used on a very broad set of designs. We're used in wireless, we're used in networking, we're used in processors, we are used in control path. We have both. Stratus is actually a product made between 2 different engines. One was called Forte out there. They picked up Arithmetica, so they're really good at data path. Not just kinda, really good at it, okay? And then we had an internal product called C to S. It was actually built off our Genus engine. It was really good at control logic. So when we bought Forte, we merged both products and came to a thing called Stratus, which can handle both very well now. So it's applicable across most designs. If you want a 20% pay increase to come out of college, learn this solution. They're very competitive to get HLS designers. I'm not joking. I've had to pay the premium. It's not fun. Okay. So automated translation, we're going to automate the translation of the design from System C into RTL. System C is a superset of C++. We use System C because you can model interfaces better than you can do in C++, for example. And we still break on hierarchy too. You would think that traditionally in C++ you use less hierarchy. We still use hierarchy here because it's important, because you got to be able to handle the handoff. You got to be able to handle the interfaces. For example, if you're bringing in a SerDes lane at 200, 200 terabytes or gigabytes, I think it is. You're not going to be able to read that in digital logic serially. You have to do it in parallelization. System C has the better method to handle and break that up. Now, regardless of whether or not it's at System C or C++, because a lot of the core algorithms in C++ we wrap with System C. We want it untimed. We actually don't put the actual schedule into the design with the System C. And we can handle both, but we recommend not to time it. That gives you the most flexibility in being able to decide what kind of architecture do I really want. Okay, System C also is much faster in simulation time. So one of the things you do versus RTL, and I'll get into this in just a second. Okay, this is kind of circling back to what I said already. I'll talk about that in a minute, what I was going to go to. But effectively, this is a survey done on the right left-hand side. You can see we went through there and we looked at, there's definitely a lot of image processing going out there, but we're in Wi-Fi, wireless networking controls. AI machine learning this is done like 3 years ago. AI machine learning is much larger than that now. It's a bigger piece of that pie for good reason. Okay. ADAS, your automotive systems, all of those. So we're in a lot of different places, a lot of different markets. Like I said, we do use it in control logic and in data path. A lot of people use this for the data path because that gives you the ability to sweep a lot of different architectures. Control logic is not all that. You can get some productivity, but it's not as fun as you can get out of data path. So, okay. So we basically take I'm going to go dive into the tool a little bit here. Okay. So we take the System C and we elaborate it and we look at the different functions we need to create. Okay. In1, in2, in3, in4, in5. These could be variables of various sizes. They could be fixed width or floating bit. We can handle both. Or floating point, whatever you want to do. Most people go with fixed width because it's lower power. We do realize that. Okay. We take this, we look at all the multipliers and adders we have to do. And we tag all those. We actually go through and we characterize these parts. We use our Genus synthesis solution, like I said, a full integration, and we go build the part. We build a fast one, then we build a small one. And depending on the application do I need a fast one, or do I need a small one that consumes less area or quote unquote less power? That's not always true, but there it is. Okay? And so you can see we got these characterizations built from, well, where do we get the timing numbers from? We actually use the standard cell libraries and the technology files from the Foundry. So I can do this with an FPGA. I can do this with a 3 nanometer design. I can do it for a 180 nanometer design, and I can use all the same System C. Okay? Then we schedule it. After we've characterized it, we just start to schedule it. What's the time period, what's the clock period? This is one of the things, the schedule and the time period and the latency are all configurable inside of Stratus. So it's not a set number. Okay, and then we'll actually build it out as a component set. Okay, we'll put the registers in to time it appropriately and put it out. Now, like I said, here's the power that you really see. This slide kind of shows you that, right? So on the top line is the example I showed you already, right? So we're basically scheduling it. Every adder and multiplier is used uniquely, and I get really fast throughput, okay? That's one of the things I can choose to do. But on the bottom line, I came down and said, well, look, hey, I can do this all with one adder, one multiplier, right? So from a power point of view and an area point of view, this is definitely, at least the initial power, maybe not so much over energy, but at least the initial power, that's better. We have to schedule it. We have a state machine we have to create for it. So we create the state machine. And we basically, we break it down to one matter and one multiplier. So the area becomes much smaller. And you can sweep somewhere between the two and figure out where's the best one. We can sweep on alternative process technologies, power saving modes, pipeline implementations. So we can actually pipeline adders and multipliers to you, and we can control the state machine for that as well. So we can do all of that inside the tool. So here's what the customers say about this. I think this is useful to see this real quick. Stratus gives you more reusable designs. That's from Socio next. 3 times the error reduction from methods to business. Another 35% better power, 51% lower than the hand-edited RTL. That's not an uncommon thing to hear. All right, especially if we give them the same schedule. Okay. We got the schedule to meet 2 times faster. This is what Elad Littman over at Intel over in Israel said. And this last one came from Elad. This design couldn't be done using conventional methods. These 2 paragraphs we hear not just out of Intel. We hear out of a lot of different customers. For example, we're at a certain customer, I can't say who because it's in flight. They're taking 4 video codecs and making them 1. And by using the same exact hardware and interleaving them. If you try to do that with RTL, have fun. We'll see you in a couple of years. They're trying to do it in, I think it's 6 months. And they're almost done. And they've been running on it for the past 3 months. Okay, so again, we can do things you cannot do by hand. For example, see that example I showed you, just 2 adders and 1 multiplier, right? So 1 adder, 1 multiplier for the design, and we only had what, I think 3 adders and 2 multipliers, something like that. Try doing that with 50 multipliers and 50 adders. Well, you can do that with HLS, right? You can use 1 adder multiplier for 50 if that's what your application allows you, it's what you need your application to do. You're not going to do that by hand and not in your head. It's tough. Okay, so this one's kind of, I like this slide a lot because it kind of steps you through what you would do in HLS. This is really good for students to see this. So the first thing we do when we start a new project, we use a project.tcl. This project.tcl, we're saying, hey, here's my standard cell libraries, here's my tech left, here's what I want to use for my clock frequency. If I want to put some latency limitation, hey, I don't want the latency to go over this, or I want it to be more than that. You're setting that up. The other thing you set up your simulations. Hey, here's where my verification environment is. We are third-party compatible. We recommend the Cadence solution, but we do allow other tools to be used. So if you use somebody else's simulator or somebody else's synthesis, we can plug in that in too. Okay? But we recommend ours because ours is better. That's where we leave it. You then write your system C algorithm. Okay? And that's usually not a long pull because you don't have to write at the detail level you have to write with RTL. Okay? The next thing you do is you verify it. This is in bold and in green for a good reason. So if you've done RTL design, you know how long it takes to build it and verify it. It's a pain in the butt, right? And you can get a lot of late stage bugs because of it, because you might miss something. Because you do it with the C system, C++, less lines of code, less areas for issues and problems. It abstracts your code and you can verify it here. Okay? We had, let's lay on this for just a second longer. We have a customer who does wireless, and then because they haven't told me I could tell you this, I won't tell you their name. And they did half the design in the Wi-Fi solution with Stratus, and the other half they do it by hand RTL. And the Stratus designs, they came in early, they were able to meet their power performance area right away in their backend solutions, and they had no late stage bugs, 0. Right, which is unheard of, but that's what they had. The RTL design barely met the schedule, lots of late stage bugs, struggled to meet power performance area. Next generation, guess what they did? They all went to HLS. They flipped it all over, okay? That's why I can't emphasize this point enough. You verify up front. Okay, after that, we verified it at the system C++ level. We actually run the high-level synthesis, kind of the step through I already talked through, okay? Once that comes out and gives us RTL, we can now start running that through analysis. We run the simulation again. Sorry, I'm tapping the mic, my apologies. We basically look and make sure, hey, does the system C simulation equal the RTL simulation? And this is what I would recommend for most companies too, is that we want them to really pound the crap out of this one so then I can simply just re-verify it at the RTL level. Now, a few things like clocks and resets don't exist there, so you do have to do some more verification here. But if you do that, if this becomes a highly validated model, it's a lot more portable, okay? And then, of course, we run RTL synthesis, we will run some floor plan prediction, gate level simulations, and we will run power analysis as well, okay? I'll go into some of those solutions when we talk the power analysis and the synthesis a little bit more, but not right now. This is our IDE. This is what we use for the GUI. You can see right here, for example, we have the different configurations for the project. These are all different microarchitectures for a given design. These are what we call simulation configurations, place and route configurations, maybe memory lives. You can play with memories here. You can decide, what kind of memories I want to use, how I want to wrap them. Do I want to use memories at all? That's all possibilities here. And that's fairly instantaneously. You can handle that, okay? We handle the synthesis configurations and the power analysis configurations here. We have hot links between, say, the system C and the RTL that gets generated. This one just doesn't show you the RTL. But we also have here, this is our CFG, I think it's I'm getting the wrong name for it, CDFG. I think it's our configurable diagram. I'm not getting the right name for it. But it's a diagram of the actual C++, and you can cross-probe too. We actually put all the metrics in here, put in a bar chart for it, and we also do a detailed analysis of each configuration. This is, for example, an area map of that could be power consumption, that could be area consumption. You can decide what you want to do. Who's my big pig in the design? Okay. Of course, you can code in this environment. You can see it's got the capabilities to do that as well. This is a good comparison. It kind of explains what's the difference between when I write it by hand and when I write it in HLS. By hand, this is what you should expect. In HLS, this is what you should expect. From an academic standpoint, I know which one I want to do. I think you do have to manage it. I think what you're going to find in that space is that some of it's going to be well done by like I said, the bits and pieces will be well done by it. But the reason why we use System C on let's say the interface, for example, is to be able to handle complex interfaces. The problem with a lot of other C-based solutions, they're C++, and they can't handle that, right? The other advantage System C gives me is I can take a System C level design and I can basically take it into my UVM environment, my Unified Verification environment, and I can plug it in and out. So I can use the System C or use the RTL, right, for the actual verification, okay? So I'm pointing that out so that gives you both the amount of flexibility. Now, we can also handle timed System C. So if you want to do some of it timed, you can do that, right? We can also handle, hey, I want to take this module and I just want to reference it. I've already built in an RTL, you can reference it. So that gives you all those capabilities. If this is a type of architecture you're interested in, we can probably have you talk to the experts about it, and you can figure out whether or not you can do it. A lot of things that we used to not be able to do, it just improves every year, right? We do more and more every year. Being able to handle simultaneous, reads and writes, for example, memories, that's something we couldn't do until recently. I'm just giving an example, right? Okay. So it has a lot of flexibility and can work with what you have today. And then over time, we work to automate that at a higher and higher level. Right. We basically have this 3D-dimensional solving space because we are looking at multiple power, performance, area, schedule, all those things, right? Basically, we're sweeping different architectures. As we look through these different things, do I pipeline it, do I not? Do I use parallelism? Do I share it? What do I do, right? So it really abstracts your quality results, and because we call these sign-off level engines to time it and get the power and get all that, you know the answer to what you're doing. Is it feasible or not? Does it give me the power I'm looking for, right? Is it going to meet within the area I need? Okay, all of those things can be answered out of Stratus HLS, and you don't have to leave it. I'll walk through an example of one where we take it from MATLAB, which I'll talk about in a minute, and take it right into Stratus. Okay? Yeah, so this is like tailor-made to machine learning. Why? I'm sweeping things, right? I'm running 27 different architectures. I'm running 100 different architectures. what are the weights that I want to put on it, and I want to sweep through on these very different options, right? Just because I have 100 different options, you realize it's 2 to the 100th. It's not 100 different things, because I can turn on and off all of those things, right? So that's why you want to employ something like machine learning. Of course, some things don't make sense to work with each other.
I meant they might do a machine.
You can build. Okay, so let's talk about this one here, okay? So MATLAB. So MathWorks came to us about 2 years ago and says, we want to integrate with Stratus because we see you guys are the market leader. And we have a great little product called HDL Coder that does okay, but we need something out there that can meet people's power, performance, and area goals and be able to sweep the designs and use different configurations and do that. And says, we don't want to build that because you've already built it. And so we said, okay, we'll work with you to do that. So when we do these presentations, we actually do them jointly with MathWorks usually. I just took a few slides and this one. I'm not sure if I'm allowed to give you all this, but I'm going to anyways. So fair enough. So what we do is we take the MathWorks MATLAB M code design, not Simulink. Super important to remember that. Doesn't support Simulink today. In the future, they may do that. They're definitely getting a lot of feedback. They're hearing that. I hear a lot of designs are in Simulink. That's why. They take the MATLAB M code design and they put it out to both the design in the System C and C++ wrappers using HDL Coder, and they put a test bench out. So it saves you a ton of time to having to go build all that by hand, okay? This is an example of what it takes to take a MATLAB-based design and build it through Stratus. So, okay, so this is an AES encoder, the one I mentioned earlier, and I have the design metrics on this when I'm done. Okay, so you can see it. MATLAB export takes about 10 minutes, not very long. Okay, the project setup to get it all set up for technologies and the project article, that's about 10 minutes. It's not very long. We try to abstract that too, so that students don't have to know everything about place and route to set this up. Right, so just be aware of that. Why? Because a lot of go back one. A lot of the customers we have don't have that experience at this level, so that's why. Okay, Stratus in this particular example only took 7 minutes. It's actually pretty fast. More complex designs is going to take more time. Okay, so the long pool is actually doing the analysis. Or we can do Joules power analysis in parallel with Genus power analysis, or you could do Genus and then pull that information into Joules. Depends on how you want to do it. They're both running fast. This is running fast synthesis. This is running full synthesis. In my experience, I would always just go Genus, run Joules. To me, it's more accurate. That's why I would go that route. Okay, but that's just my experience. And then we are able to run it. Now, so basically, and this can be, at this point too, it's all in parallel, right? I don't have to run one architecture. I can run, this has got 5 different architectures are going to run. Okay, and really we're just looking at the pipeline throughput. All right, so 5 explorations, 20 minutes human time, compute time is about 20 minutes human time, 2 hours compute time. All right, this is an example. Now the hand-coded design was about 20K, and the reason we didn't rewrite the hand-coded beyond the one stage here is because it takes time, a lot of time. Okay, so that's why we didn't bother to do that. But you can see right off the bat, even with the pipeline throughput of 1, we have better area, and I think it had better power too, right off the bat using 1. Now we had a System C system 1 built as well here. So we went them from MATLAB to System C, and then we had built it in System C as well, okay? And what you can see here is that even though the MATLAB is a little bit, actually this one's actually pretty competitive. In some cases it's a little bit bigger. It's fairly comparable in what you can achieve out of both of them. And I expect over time that this gap that you see here will get smaller and smaller. This is our first integration with MathWorks, not the last. Okay? So this is just showing, hey, out of the box, what am I getting right now out of MATLAB? I'm getting pretty competitive designs, right? And then what I'm seeing here is that, okay, if we did it by System C, we could probably get this. If we went MATLAB, we're getting this. Depends on what I need to do here. And over time, MathWorks is actively working with us to improve these metrics. This is just one design, for example, though. For example, we had a design where we took one of these SerDes transport that we're doing an optical transceiver, right? And we're trying to go through and process the SerDes interface to it. And they were running it at 16 lanes, 500 megahertz, at 5 nanometer, for example. And we said, okay, well, we have this in C++. We said, well, or System C and C++. So we said, okay, we can sweep that. We can look at what does it look like for 8 lanes at a gigahertz, get the same throughput, or 4 lanes at 2 gigahertz, because 5 nanometer can handle those speeds, right? And the truth is the highest power consumption and almost the highest area was the 2 gigahertz 4 lanes. And that's because of the sizing on the gates that has to happen to meet 2 gigahertz. And think about it, we cut the design in half, in a quarter of what it was, and it was one of the biggest designs. The sweet spot of it, by the way, was the 1 gigahertz 8 lanes. It's definitely better. The process doesn't have to push so hard to meet that timing. So, yeah, you know, a 1x gate is a lot smaller than a 12x gate, okay? Yeah, that's what it comes down to. That's why it's not straightforward anymore. In general, this is definitely taking the market by storm. A lot of people are interested in it and are starting to heavily look at this as well. It's keeping both MathWorks and ourselves busy. So, okay. Another QR code. If you want to learn about more customers' experience, this is many years of experience. Take a shot of this one, save the web page, go look at their different design, what their experiences are. It's really good. Okay, I'm going to move off of HLS and go into RTL synthesis. That sound good to you guys? How much more time? Okay, so I'm good on time. I should be able to do the next one in the next hour, so we'll be all right. Okay, Genus, some of the key functionalities in this one that we've put into over time. So you know you're basically taking your RTL and you're synthesizing the net list into a net list into gates, okay? And I'll walk through a little bit about what it does and how it works, right? But some of the keys to our technology today is we use physical synthesis today, that pushing up a place and route gets pushed up into our synthesis solution. So after elaboration, we're looking at placement immediately. Why is that? So wire delay versus cell delay. 180 nanometer, right? Wire delay versus cell delay. Majority of it was cell delay, like 90%. Okay. Fast forward to 28 nanometer, right? Wire delay versus cell delay is about 50-50. Okay. Go down to 16, 70-30. Go down to 3 or 5, like 90% is wire delay. That's the truth. So it's completely changed the model. So you have to know placement so you understand wire delay early on. You're right. So that's why I would tell you start higher up. That makes your life easier. Hey, look, that's the whole point of that HLS thing is, look, a recent hyperscaler account, very big, you know who they are if I told you who they were, but I can't. They said that we love HLS. Because it puts, you know, all the things I said before, but said we had a timing problem they couldn't solve in back end because, you know, HLS is still high level. You can definitely run into problems that you can't predict yet. Well, they said we told them about it, and the next day we had the new code and solved the problem. You need to run it. You're welcome to do. That's no problem. So anyways, this is some of the key technologies. Physical synthesis we put in here. Our Compass compiler, we're looking at problems right at elaboration and in what we call generic optimization. We're not waiting till later stages. We're not just saying, oh, we'll just elaborate the design and then optimize it. We're saying, no, we have to optimize as we elaborate and as we do the actual generic gate optimization. And then power. Power has become probably one of the most critical things. If you talk to some of the people doing high performance 3 nanometer design, power closure is tougher than setup closure. So setup closure is, do I meet the frequency? Do I meet the timing, right? Can I meet 4 gigahertz, right? Well, yeah, they can meet 4 gigahertz, but can you do that and create a power problem for yourself? Where you have too much IR drop or too much thermal and that thermal being drained, all right? Too much heat in the given area. So those have become integral in solving this problem. You have to look at both power consumption and the energy consumption over time. Okay, so these are the 3 kind of key areas we've been focusing in Genus as of late, as well as heavier and more integration to the back end and into our power analysis. So this kind of walks through that a little bit more about how, like I said, the heavy integration. What we do inside of it, we basically run the RTL compiler. When we run synthesis, we run 3 major steps, or 4 major steps. We elaborate the design, so we take the RTL and we put it into something that's more readable by the machine. We unroll for loops. We expand multidimensional arrays, things of that nature, right? Then we map it to generic gates. This is a generic technology, okay? And then after that, we then go into what we call SynMap, or we map it to an actual technology. And then last but not least, we do optimization to that given technology. Now, optimization actually occurs now throughout that whole process. It doesn't occur just at one spot. It happens throughout the whole process, okay? But those are the 3 major steps happening way up here at the synthesis level we're talking about. This handles the generic and the mapping. This handles the optimization side. In optimization, this is full place and route. So we're actually placing it down to the detail level and routing it as we optimize it, okay? As we continue to push all that down into what we learned here into place and route. What we've also done is we've said, okay, hey, this has got some really smart technologies like CC-op, which is our clock concurrent optimization. I'll talk about that later, okay? But this does things like useful skew. I'm pushing that up. I can call useful skew now in iSpace so I can see how much time I can borrow between different pipe stages, for example. Okay? This is the Compass compiler. We're doing some trade-offs here. We're looking at different characterizations of microarchitectures up front, and we're trying to solve for the global solution. What is the best point on the graph that I should actually put the actual RTL implementation out into since in generic? All right, we do this up front. Trying to find this as RTL, and we did this a couple years ago. This continues to get better and better. So even if you give us crappy RTL, we can solve those. My suggestion is to fix the RTL first, because you'll be in a better position, but the reality is we solve crappy RTL. That's really what it does. Okay? This is what's called the global mapper. This is really fundamental to the technology that we use, okay? So we look at the standard cell library, we look at the logic that you want to create, and we work out the best case timing, and we set targets. And we look at the targets can be both timing, power, and area. And those numbers get set on every gate, on every device. If you run Genus synthesis, you'll notice that a lot of the things have this G number on it, on the gate. That's actually the weight they're using to optimize it. So I don't know how to translate that personally, but that's how they use it. Okay, so they do that in the solution. Why is that useful? Because now we're looking at the targets of that G number earlier on in SynGeneric, SynMap, and SynOpt, and we're constantly trying to improve setup power and area throughout the whole process. So one of the things that Genus came out to the market right off the bat was what we call total native slack, or number of failing endpoints. Right out of the box, we go after that total native slack of failing endpoints, not just the worst case path. Some of our competitors, when they first came out in the market, they would not handle it that way. They would go, let's build everything, and then we'll just whittle on every worst negative slack until we get down to the bottom. We said, no, we're going to do this all up front. That's how Genus handles it. And we'll get into a second, how does it handle that on a large scale design and do it very quickly? So we'll talk about that in just a second. Okay, so Genus, go ahead.
Can you tell about G number? What does the weight of stands for? What does it do?
It's an actual weight for your timing and your power and your area. For and that's the G number for the generic gate they put in there when they actually map it to an actual gate up front. Yep. So, good question. No. Okay. So as we're mapping this out, we're looking at all these different places here. We're looking at how do we save area, how do we improve timing, and how do we save power. Now, one of the things here to keep in mind, the tool is first of all going to meet timing, because if you can't meet setup timing, you can't put it out the door, right? So you can put all the power weights you want on it. At the end of the day, it's got to meet setup timing, right? So you can't go in and say, well, I'm going to fail timing and I'm going to have it meet power. If that's the case, you need to either rewrite the architecture, or you need to give it more time, right? You got to give it more clock cycle time. So fair enough. Okay. All right, now Genus is, we go through what we call a partitioning algorithm. We'll take an RTL design and not just run the whole thing. We will actually start looking at how do we split it across different paths and partitions so we can actually start optimizing it. So all of that global optimization is we're looking at doing gate transforms and optimization across these different places. Do I use this type of adder? Do I use that type of adder? We're doing that all in parallel and we're separating all that out. We have the ability to do that at the micro level. So we take a module and we go, okay, we're gonna break apart this module to 100K instances, 50K instances, or even 10K instances. So they can split it across that way, all right? And then we can actually do the optimizations in parallel too. So for each partition that I break it down to, depending on what the size of the design, depending on how many CPUs and everything I have, I can now look at every optimization I have in parallel too, okay? Remember that Compass compiler, all those different graphs it looks at? Those are looked at in parallel. They're not looked at in serial. Why not? There are two different problems and where they take you, so look them at in parallel. All right, where is it going to take my architecture when it's done? Okay. Now, some of the new things we've done, we've actually implemented because of the heavy push on, it's now wire delay dominant and not gate delay dominant. One of the problems you run into when you're doing early RTL designs is you don't have a floor plan because it doesn't exist. So we put the capability to build a floor plan inside of the design. We used a thing called GigaPlace Excel. What this does is GigaPlace Excel is our automated floor planner in our P&R solution. People actually use it to place memories and macros in a given design, as well as the pin placements and all that, to try to make it more optimal. And they will actually use that to tape out the design. So what we said is, well, let's just take a generic form of that so they can run it really quickly and put it up all the way at RTL synthesis. So at the RTL block level versus, say, the implementation level, I can get a very quick design and get a fairly decent estimate of power, performance, and area by using real-world placement and real wires, okay, based on a simple floor plan. So what do I mean by RTL block level and implementation level? So think about it. When you build an RTL block, it's probably somewhere between 2 to 50,000 gates or instances, something like that, okay? The P&R solutions run at 2.5 million. This is kind of the sweet spot, 1 million, 2.5 million, 5 million, 10 million instances, right? That means it's multiple hierarchical RTL modules. So this is really good at taking at the RTL block level and building a quick floor plan and giving you a very high accurate estimation because we're looking at a small piece, okay? Now, but do you realize that 2.5 million, 5 million instance level where I have the many blocks and all that, we use the same technology to actually build that floor plan too. So you get the benefit of them figuring out the larger problem down to the small level. We actually integrate this all the way up to HLS too, for a good reason. So those 100 of microarchitectures, I can have 100 floor plans built for me real fast and get real accurate estimates. This is mentioning, like I said, we do physical optimization all the way at the generic gate level. We actually place it and we route it. Now, what I mentioned about, remember how the metal stacks, I mentioned this before, that the top level metal stacks are more capacitive and are less resistive, and the lower metal stacks are very little capacitance, highly resistive, right? So what metal you travel on makes a big difference. I know it's your timing and power, with your timing, your power consumption, how far you can drive something before you hit your slew rates and whatnot. So what we have done is we have an engine that's smart enough to understand what layer am I traveling on. It's not just routing, it's routing and what layer am I on? And it goes, okay, well, this is a really critical signal that's got to go a long distance. Well, that probably shouldn't go on metal 1. That should go on metal 9. And we make those decisions. And it gets passed forward as we do that. Now, we'll reassess those decisions over time, but we absolutely do that. So we start at the generic gate level, making those levels decisions. Okay. I mentioned the full stages here. We use what we call slack-driven placement. So you might have heard of a concept called timing-driven placement. Timing-driven is looking at wire length and timing from one register to the next register. Okay? Although that sounds good, it's problematic. Because in reality today, we don't do timing just from one register to the next register. We look at throughput which is the input to one register, to the next register, to the next register, to the next register, before we go to output, or we circle back on ourselves, right? And that's the difference between timing-driven and slack-driven. In slack-driven, we're looking at the entire problem. We're looking at how much trade-off I have for slack for the whole process, and versus in timing-driven, I'm only looking at a given single path, right? So we moved to a slack-driven placement algorithm about, I want to say 6, 7 years ago is what we moved to. It made a world of difference. So if you do like a digital signal processor and you hand place it, you're going to put a register, your combinatorial logic, register, combinatorial logic, register, combinatorial logic, right? And that's how you're going to handle it, right? Or if you retime it, you put all the stack, you put all the registers here, and you let the thing figure out where it needs to put it throughout the whole stack. If you look at the placement of a digital signal processor today in our slack-driven placement, it looks just like that. They may not be on the same rows and all that, but that's how we build it out, okay? And that's because it understands the total slack that you have to solve over the whole problem, okay? We have concepts now what we call critical chain timing. So we don't just look at WNS and TNS, we look at what's the critical chain. Critical chain is that input multiple registers to the output, okay? Okay, this, I don't have a lot of slides on DFT. I'll just walk through this one just briefly. So we fully integrate our design for test technologies. Design for test, we're looking at scan insertion. Are you guys familiar with scan insertion, for example? You know why it's done? The black magic of DFT? Anybody? No? No, DFT. All right, so you build these billion instance designs, right? You have all these transistors in it. How do you know it works? Physically, how do you know it works? Right? You're not going to take a little probe and test it. That's not happening, right? So they build in a ability to test it, is what they do. So on every register, they will have an input to input a vector, a 1 or a 0, if you will. And then they'll take that vector and apply it to the combinatorial logic and process it, and take that output of it and process it back out to the next register, right? And by looking at the patterns from one register to the next register across the whole design, you can ensure physically the device was built properly, right? Super important. Scan, right? You have to have it. I still have customers, believe it or not, who do not believe in putting scan in. I don't get it, but that's because they're doing some test chip. I don't need that. I'm like, really? I mean, you're building 1,000 devices. Yeah. Don't you want to know if the thing works? But they don't. There it is. But most people to put in scan nowadays. It's a very design for test, a very common piece to put in there. They use what they call automatic test pattern generation, or ATPG, to build those test patterns. The ones I mentioned, we inject it and you check it on the outside. A logic built-in self-test engine is a pattern generator and a comparator. So instead of doing that off chip to check your yields, right, you do it on chip so you can make sure it's working in system. It's pretty hard to do an in-system test on a satellite that's 300 miles above us. It ain't happening. So you do logic BIS for those on purpose, for example, okay? Now scan, if you think about it, they use what they call scan chains to stitch them all together. And they have them, and if you have a 500K instance design and you say it has 10,000 flops, those scan chains, if you have 10,000 flops, you divide it by 100, that means you're going to have basically 1,000 flops per chain. Not such a big deal, right? You can probably process that if you're doing it in, say, because those run at slower speeds, 50 megahertz. You can get that done pretty fast, right? Okay, so think about that scaled up to 1.6 billion. Right? Not happening. Right? It takes a lot more time on the tester. Tester time is money. They charge you for this. It's not free. Right? So being able to get through many chains over time is what you need. So we do two things. We compress the test pattern coming in so it's smaller to read it in, and we decompress it on silicon. And so we can put it out to the design. That enables two things. One, to have less scan chains overall, or actually allows us to have more scan chains overall, but less inputs to the design, right? Having 10 inputs to a piece of silicon to measure it is great, but you have a 100 million instance design, and I want to do I want to put 100 inputs just for scan? No, it's very expensive to do that. So they still have 10 inputs. They just compress them. That's how they handle it. Okay. So what we do with this, we have our DFT engine has the ability to compress it. One of the things that kind of differentiates us versus a lot of competitors is our compression engines are not built in one place, they're built throughout the design. So if you take your compression engine, you center it in the middle of the design and you spread it out to everywhere else, it's a pain from a routability point of view. But if you take it and spread it through the whole design, it's much easier to manage in routability. We also have thing called 2D elastic. It allows us to compress do even more higher compression ratios. So most designs can do about 200x. At 400x, you see a lot of congestion. Well, we can push 800x with very little congestion because of the way we handle the compressor. Okay. And of course, you want to be physically aware about where you put all these scan chains, how you stitch them together, where you put all the compression logic. So that, remember, placement routing integrated to Genus, so we can do all that together. And that's why all that becomes critical, especially in test. All right. I mentioned physically aware scan stitching. If you don't do physically aware, what ends up happening is you get a mess of nets going every which direction. Okay. From a hold time point of view, that's actually nice because you still have to pass hold time on scan. All right. And remember, hold, if you will, is frequency independent. So it doesn't matter if it runs at 50 megahertz, you still got to meet hold. Right. So from a hold time point of view, that's nicer, but from a routability point of view, which is usually the bigger problem, it's not. So we actually need to have the ability to physically stitch them so that chains basically go from one, these are memories, from one memory to the next, or they go from one set of registers to the next. They basically go in a straight line or row by row, okay? So it reduces that over wire length. Okay, so let's jump into power for just a minute, and then after we talk about power, we're going to go into place and route. Okay? So we mentioned this earlier. We have this Joules power analysis solution at the RTL level. It is a level. It is really not just a power analysis solution, but it's a power profiling solution and a power optimization solution, and I would probably venture to say a vector processing solution as well. So for example, when you find where's my peak energy, how do I translate my peak energy information from RTL to gate level netlist without having to actually run gate level sims? So most of you are probably familiar with running RTL level simulations. They run relatively quick and easy to do. So if you run the gate level, you have to take the same test bench and feed the gate level and make sure all the inputs are correct, you haven't missed any models, and then get the timing information from the back end and then feed that back in. Usually those are two separate different sets of people, which means it takes more time to put all that together and it's more difficult to do. Okay, now if I talk about Stratus, it's easy to do because it's all encompassed and automated. If you're talking about an individual or a team, it's not so automated, right? It takes more time, it's very difficult. And if say I wanted to do it after synthesis and after place and route, it's very difficult to do. Right? I have to basically the synthesis guy has to put it out. I have to go run the cycles to come and bring it back. Why do I bring all that up? Because in what we do with Joules is we have the vector processing ability. I can take an RTL level stimulus and I can put it on the sign-off design. It's pretty much that simple. Okay, and I'll walk through a little bit more what we can do with that. It used to be you'll lose all the combinatorial logic annotation, if you will, between RTL and the gate level netlist, because obviously the combinatorial logic in RTL is, A equals B or A plus B, right? And in the gates, it's actual ands and ors and adders and all that, right? Okay, so you lose that annotation. So that's how it used to be. This is actually talking about this flow called replay, where we're able to replay both the vectors on inputs and outputs in all the registers. And then we use the statistical model to try to solve, okay, how much power do I consume in my combinatorial logic? Okay. But what we've gone to now is what we call glitch power analysis. And this goes to what we call a full level of gate level simulation built into the Joules system. We call it X replay. So we do the same thing we did before. We apply all the vectors to the inputs and outputs of the registers. And then we said, well, hey, we own a simulator, a really good one. Why don't we just call that under the hood and let it simulate out all the registers real quick and basically annotate all my combinatorial logic and stop guessing to what the actual switching is. So I can do it 0 delay based, or I can actually inject the what we call the standard delay format, and I can do it with delay based. Now, why is delay based important? If you look at a combinatorial chain, okay, an OR, and an inverter, right? At any given time, when the registers come in and they're switching, it could be at 1 or it could be at 0. At some point, they have to stabilize out so we can meet setup time, and they have to stay long enough to meet hold time, okay? But during the time that we're trying to get there, that period of time, they can switch a lot, right? And when they switch, they consume power. That's what we call transient glitch or glitch power, okay? And in some designs, it's a very small amount. In other designs, especially data path-centric designs, it's a lot of power. It's like 20 to 30% of the power consumption. So understanding where your glitch power is coming from will let you make better decisions on, do I take this highly glitchy circuit and put it in the critical path where it's switching all the time, or can I logically actually move it down to a different point in the logic cone so it doesn't switch as much? And those are the type of decisions we can make because we now have the gate level SIMs. The problem we used to run into is that, okay, we can solve that problem optimization-wise, but how do I get the gate level SIM, right? Because it takes that long process, it's a pain, it's a big loop, and it's not easy to do. Joule solves that problem. Sorry, I'm covering my mic again. My apologies. So Joules will solve that problem for you. It'll actually go through, replay all the stimulus, and actually run the gate level SIM like I mentioned before. And it's a real game changer. This is you might not think it's a lot, but 3 to 5% power savings using this type of engine is really important. And this is what we've just released in this past year, and we're actively pushing it out to different teams, different companies out the world. So it's in production now with many companies already. So. Okay, so this is also mentioning we have an integration with our emulation solutions. We have 2 levels of emulation solutions. We have a processor-based one called Palladium, and then we have a FPGA-based one called not Excellium. It's not on this slide. When I remember it, I'll let you know. But they have Palladium, and then with that, of course, we work with our simulation solutions. The Palladium and the other FPGA-based solution, Protium, that's the name, both use a similar format called the PHY format and a binary format. So we hand off the PHY format instead of a VCD file. And if anybody here has worked with VCD files, they're a pain, they're huge, they're massive. They don't support like 2-dimensional arrays, and they're really limited. They're an old technology. So we hand off binary databases now. So we can hand off those binary databases directly into our power analysis solutions, and we can look at it. For an emulator, they build massive amounts of vectors, so even Joules doesn't like that. So we'll look at a activity profile and try to figure out where's my highest peak activity, that gives me peak power, and where is my steady state of activity where I would look at my energy consumption. And we look at and we analyze that. Okay? So power and energy, definitely concepts you're going to be facing out in the real world when you come and graduate. So remember that, power and energy. How much power do I consume? What's my peak? We're looking at thermals, we're looking at IR drop, right? Energy, how long does my battery last? How much am I taking off the grid so I don't brown out the neighborhood? I mentioned this one earlier, conformal, briefly. Conformal is basically our static analysis checker as well as our logical equivalency solution. I'm going to steal some more water here. That's what happens when you talk for an hour and a half straight. We use it for these different checks. This includes low power. What we mean by low power is that today a lot of the different engines will use techniques like power shutoff to save on leakage, or they'll use multi-supply voltage, where one part of the design works say at 1 volt, and the other part of the design works at 0.8 volts. And so you have to be able to manage that because there's a lot of physical things you have to deal with. For example, in power shutoff, if you shut a domain down, you can't just take the outputs and drive on it into all the inputs. You're driving X's, and those X's will switch, right? So you actually have to drive them to a certain state, usually to 0 or 1, so that they actually don't impact everybody else down the line. So that's a physical attribute you want to put in there. They used to have to do all that by hand, by an RTL, but we integrated things like power intent formats to manage all that for people. It's still very complex, but it's much easier than doing it by hand. We do SDC constraints. SDC stands for Synopsis Design Constraints. It's their format. It's where you create things like clocks and uncertainties for the clock for your different power domain, different clocking domains, if you will. Your input-output delays, what we call exceptions, where timing doesn't matter. You do a set false path, or you need more than one cycle because it doesn't switch or the data doesn't switch every cycle, even though the clock may be running every cycle. So multi-cycle paths, that's all get defined in the SDCs. We have checkers for that. Okay. All right, so before I move to Innovus, so any questions on RTL synthesis or power analysis or our static checker here, conformal? I won't give it an actual percentage because I don't know that number. It's a fair question. It's very, in the US is lagging behind in other regions, right? Like in Asia, they use a lot more HLS than they do here. It's probably on the orders of 50%. It's a lot, okay? Here in the US, we're still pretty dragging our feet because the comment comes in, well, HLS doesn't do so great on combinatorial logic, and just give me that big bang up, not combinatorial, but control logic. Yeah, that's great, but most things today are data path centric. They're not combinatorial. And HLS shines in the data path centric portions of the design. And I think that's where the difference comes in, is that in the US, we need to wake up a little bit. That's the truth, okay? HLS designers are worth their weight in gold. The amount of work you can do as an HLS designer is much more than you can do as an RTL designer, and that's the truth. If you talk to people who are RTL designers, we should bring Dave Garrett out here. You ask him, why don't you code in RTL? And he goes, why? Why would I bother? I can do it so much faster in RTL and HLS. That's why, right? The ones that are seasoned veterans know this, so they don't even bother. It's also, I think the other thing is it's a knowledge multiplication too. So to become a really good RTL designer, okay? You're going to be doing it for 10 years, right? HLS has all that knowledge built in. Why do I have to figure that out, right? Let it do it for me, right? Figure it out. So you need to have the baseline. You need to understand what it puts out. What is the RTL design? What would be the optimal structures? Those are important to know that, right? How to get to how do I get to where I want to go to? But beyond that, after that, let the HLS, still messing with the mic, apologize. Feel something here and going, what the heck's here? That's what's going on. Beyond that, you want the HLS solution to solve that problem for you. And so I think that it's really smart that they're thinking about a class here. They really need to leap. There's other colleges have been doing it for some time now, and they really, they're ahead of the game for you. So, let's get there. I think that's what you want to do is really push on them. So. Any other questions on that? I'll start talking about place and route. Okay. So let's talk about Innovus. When Innovus started out, I think it had about 40% market share, something like that. Okay. It's not 40% anymore. Innovus is now the dominant place and route solution in the marketplace. There's a good reason for that. It's got a lot of good technology built into it. We've hired a lot of smart people to build it, okay? And they build it better every day, every year. They're pushed on both algorithmically solving it better, as well as putting it out faster. And so by doing that, we improve our throughputs every year. We improve our ability to handle more and more complex design. Like I said, 3 nanometer didn't get easier, it got harder, right? 18 angstrom won't be any different. 2 nanometer won't be any different. It's just going to get harder, right? If you go to 3DIC, we already talked about what's going to happen if you go monolithic. Now you got to handle 2 levels of placement and all the routing and all their differences. That's tough. That's not easy. That's an NP hard problem, non-polynomial. So there you go. The reason why we started putting in things like machine learning is we realized, hey, we're already doing a ton of machine learning internally, but we always run into some point where You run into some optimization where it's, for this optimization to work, it depends on this design. It depends on this portion of it, whether or not I should turn this on or not. So machine learning allows us to go through and go, hey, well, let's just try it out. See what the end result is, or see what the partial result is. How does that weight through the process? And it allows me to learn, and allows you to learn to figure that out. Like I said, most designers, when you start out, when you do, say you do implementation, you run synthesis, you run floor planning, you run place and route, and then you go run it 50 times between every RTL drop you get, right? Well, the advantage here of machine learning is you don't do that. You get the RTL drop, you say, oh, I want to try 3 different floor plans. You feed that to machine learning. Go tell me which one gives you the best result. Oh, I want to see where all my bottlenecks in for the RTL design are, so I can figure it out. You give machine learning to go do that, give me the most optimal performance you can possibly give me, and let's go feed that back to the RTL designer to tell him where his speed paths are, right? Allow machine learning to do that work for you. That's really what the push is. We will see more and more of that as we continue to go on. It will be, I think we will see in the next 4 or 5 years, very, very quickly, at least at all the major corporations, that's every design. You're not starting the RTL by pushing it through place and route. You might push it through once, but after that, you're automating your exploration space, and that will continue to happen. Okay, but let's talk about core engines for a minute, about how place and route works. Okay, first technology when we talk about is GigaPlace. Okay, so it's a multi-objective numerical placer. Okay, it optimizes multiple cost functions. Cost functions like power, area, timing driven is still weighted in there, slack, across multiple paths, multiple places. So all of those things are weighted out, okay? Fully slack and power driven, so it's trying to optimize them both. Remember, you want to use that Joules engine, and we do this now. We inject the glitch-based stimulus in here so it knows where all the switching is, and now it can optimize the power accordingly and restructure the logic accordingly to make that happen. And that changes over time at every optimization step. So you still have to keep feeding that forward. Okay? Mixed mode means that we can do both standard cells and things like memories and custom I/O, custom blocks, for example. So if you look at a standard traditional place and route block, it looks like this. See how the memories are all kind of banked out, right? What we've started moving towards is more of this scenario where it's more of a, you can move them and we can put logic between them. We found that to be more optimal for wire length, and hence if you lower the wire length, you lower the capacitance, which lowers power. And wire length, smaller wire length also means better setup and hold timing, or at least setup timing. Hold usually gets worse, but fair enough. So that's why we use a mixed mode placer. Same placer we use in the Genus early floor planning solution, like I mentioned earlier, okay? This supports hundreds of macros, okay? IR aware, we can start looking at the current, how much current, based on the switching I fed it, which is glitch power based. I can see how much power I'm consuming on all these different places. And then sometimes you can't avoid the high switching. So what you want to do is you want to have those be less dense, have less things switching around it, so you don't have the current drop problems where it goes beyond the characterization of the library and it causes you thermal problems later or cause you setup timing problems later. And of course, we support all the advanced nodes. After 28 nanometer, it got tough. It's the design rule space like exploded, right? It used to be, okay, here's a wire, it has a width, and it has the spacing to the next wire, right? That's probably what you've seen so far in school, right? That is not what it looks like in the industry. It's the spacing between the wire on the same mask and the spacing between the wire on the next mask and the spacing of the wire next to the corner or the edge, so you don't create a problem in lithography, right? And make sure the V of this layer doesn't overlap the V of that layer. It's very, very complex. Okay. So advanced node, that's just wiring. I'm not talking about transistors. Transistor level is even worse. Okay, so we're going to go to the next major engine in here, which is called GigaOpt. Okay, GigaOpt is our engine that allows us to do. There are various types of transformations for optimization. I'll kind of walk through them just a minute here. We share these engines. So one of the things that really, GigaOpt actually came from Genus. People don't know that, but it's true, it did. Right? All the transformations we learned how to do in synthesis really well, we can do very quickly, We said, well, why don't we just put that in place en route so we can do that fast as well with more and more information. So we did that. So that's why it's called GigOpt today. So that's why it's shared, but the reality is that it came from Genus in the first place. Not commonly known, but it's true. We do power-aware transformations, of course. We talked about this a couple of different times. One of the big things we do nowadays is we do multi-bit flip-flops. A lot of the 28 nanometer belows, they don't just run a single flop. You can get a flop bank of like 8 or 16 or 4 to combine all the flops together. It has a couple of key things. One, it can lower your clock power, it can lower your clock density, and it can improve your hold time closure for DFT, depending on how the flop's set up. Why is it? Because you have, for 8 flops, instead of having 8 scan inputs, you got 1. So, and hold time is guaranteed within the flop. So that's why it's advantageous. That's one of the reasons it's advantageous to use flop banks. Okay? Congestion is something we always have to look at and be aware of. We look at density, we look at the DRCs around something. If it's a high input cell, we actually might do what we call cell padding. We actually say, hey, I have 6 inputs on this cell. I probably don't want to put 5 or 6 input cells right next to each other, especially with very complex DRCs between triple pair patterning mask. I probably want to spread those out a little bit. So we actually will automatically do that now. We'll automatically spread it and look at how many wires want to come to a given area and do those things. That's been in place for a long time, but it keeps getting more and more detailed every year. They have to deal with this problem because it gets more and more complex. Think about it, for now you have 2 different heights of cells, and 3 different heights of cells actually, and you have to solve that same problem. It's a lot harder nowadays. So placement has to be that congestion aware even in that scenario, and it's tough. And we know how to do it. We obviously can restructure the logic early. You know, when you look at a given multiplier and addition problem, you can decide where and when I want to do the multiplications, when I want to do the additions. So we can restructure that. We can restructure that, or obviously in synthesis we do it a lot. But we've also learned that, hey, we can do this pretty far down in the optimization stages too if we need to. And if we found it, hey, at the closer to the end with the clock tree implemented, it makes more sense to do it another way. We can actually change that. Okay. Useful skew, I've mentioned this a couple of times, where we look at the total slack of the whole design, and we can now push timing from this pipe stage to the next pipe stage, or backwards that way. That's done for both setup time and power, is what they do it for, right? So if one particular pipe stage has a very tight timing, we talked about it earlier with your professor. What's going to happen with all your gates in that tight timing? They're going to be max size. They're going to be really big, right? Which means they consume more area and consume more power, okay? But if I give it a little bit more time and I can use smaller gates, right, by time borrowing from the previous slide, which had tons of time, right? I don't have to consume so much power because I don't have to have as big of gates. So both setup time and power benefit from useful skew. Okay. I mentioned layer awareness as well. You know, like this is like 180 nanometer. This is 45 nanometer. Sub 45 nanometers is this big V shape, and it keeps getting smaller. If the FinFETs got smaller, you got to connect to them somehow. It means you can have highly resistive wires. You want to be on those very quickly and get off to the next layer, Well, if you did that to every single connection, you push them all up to the top layers, you're going to run out of room. So you can't do that. So you got to be able to figure out who has to stay down and who has to come up. So I have to be layer aware. When you're layer aware, your optimizations have to understand this too. If I buffer on metal 9, it's different when I buffer on metal 3. Okay? Our engines understand that inherently. It's part of our algorithms. Okay, so CCOpt, I've mentioned this a couple of times. We have a couple of different ways you could run it. These are the 3 different ways you can actually build CCOpt. One is what we call standard CTS. This uses what's called a cluster-based clock tree. Takes the cluster of flops in the given areas and then builds a tree out to them. That tree, if you look at how it builds, it looks like an H tree, but it's more spread out. Okay? And you really look at things from the center of clusters and not from the center of the design. It's just kind of how you approach the design. It's a little different. Okay? But it's very efficient. It works really well. It's very power efficient. And you can leverage a ton of useful skew. Because usually insertion delay is a little high, so you can pull back insertion delay in some places, and you can push it out in other places. So it's useful for that. The downside to those type of trees with a large insertion delay is on-chip variation. Who knows what on-chip variation is? Okay, so two chips, you can have a slow part or a fast part or a typical part, right? We understand that, process variation. Everybody get that? That's why we do our setup and hold at 2 different temperatures and 2 different parts, right? So fabs can build parts faster, depending how they process it through the fab, or they can build parts slower. They try to skew it certain ways to get you more yield, but they don't always have control over that. Over time, basically what ends up happening is you get the statistical variation, right? Everybody understand what a bell curve is, right? Yes, we took statistics. No, you might want to. Statistical variation is important in what we do, okay? But the point is that the parts that are on one extreme is the fast, and the other extreme is slow, and the typical is right in the middle of the bell curve, okay? Foundries do try to skew it one way or another, but they don't always have control over it. So to get the most yield of parts, we look at timing from setup from what's the worst possible time it would take to get there, and we look at hold, how long the data has to stay on the register before it has to be clocked, before it can get clocked away. We look at it on the fast parts. Right? That's a simplistic model, but that's what we do. Okay? On-chip variation, so that's chip-to-chip variation, right? One part could be this, one part that. On the chip, there's a lot of variation as well. So you can actually have on the chip like a 5 to 10% variation of one device versus the other device, and they can literally sit right next to each other, or they can be across the die. Okay? What does that do when you build a clock tree? That means you don't have, you will always have some type of skew. So when we build a clock tree traditionally, we try to build it so that there's no difference between when the clock arrives at clock A versus flop A versus flop B. But the reality is that with on-chip variation, you don't have any control over that, right? This is going to be 5% different than this guy, right? So you have to understand that. So on-chip, when you have large insertion delays, multiple stages, you're going to have more on-chip variation, and that's the downside to that. That drives up your flop count, usually, not your flop count, but your hold time violations, because more skew usually means more hold. And it becomes the bane of your existence when you're trying to close timing on a very tight timing. So what do? We start implementing solutions like a flex H tree, where they use very large drivers and try to build it so it distributes out for the whole design. Or we use a clock mesh. We use multiple drivers driving the same net, right? This is basically, the way this is usually modeled as a zero delay. It's not exactly zero delay, but it gets pretty close. They spice model those and they stick them in the timing solution, okay? Your clock tree solution better be able to handle both, because we can see both of these in the wild all the time, okay? There's also other clock tree solutions. These are what they call multi-tap, where you have a clock tree and you tap off of it and you build it, the clusters get built off underneath that. There's also other ones called ribbon spine. There's a couple other ones. These are the ones that we can build this automatically. We have support for this, and all the other ones we support as well. It just depends on what you want to do. But multi-tap allows you to do that. So it has to be able to handle that. And you want to be able to do useful skill time borrowing, whether you're building standard CTS or you're building an H tree or a clock mesh. One of my first engagements on CCOP, which was about 7 years ago, was with Intel, and they used all clock meshes. They're like, well, you can't use useful skew to improve my design. We said, let's try it, and we did, right? Because they still had a couple hundred picoseconds dropping off of that, and I can improve it by 20, 30 picoseconds here and there, and that made a difference when you're running at 2 gigahertz. So that's what it came down to. All right, NanoRoute is our key routing technology. I'll try to wrap up here real quick. It's highly distributed because you can do many routes over many different CPUs, over many machines. It's very scalable to our DRC, like our DRC engine is. It handles all the advanced nodes, the many different masks. These are showing you 3 different masks here. Okay. It has timing and power. It was aware of the timing and power. And we have the ability to do things like bus routing, coaxial shielding, differential pair, capacitive matching. That's our high frequency router. So something might be useful for some of you guys in some of your PhD projects. If you want an automated solution to do coaxial shielding or differential pair, we have that all the way down at the standard cell level. Okay, and I think, okay, yeah, so this is integrated sign-off engines. This kind of goes over this here. Look, so I mentioned this earlier. We integrate basically our sign-off timing engine. This is our STA. We have this fully integrated into Innovus, both from a timing perspective and from a ECO closure. We have the same thing for IR drop. We can look at IR drop, and we look at power integrity throughout the design. Of course, our RC extraction better be embedded, otherwise you have no idea what your capacitance resistance is. Our DRC model, our LVS DRC is fully integrated here as well, along with metal fill, which is super critical, those lower process nodes. And of course, everybody reads off the Liberate characterization engine. And I think I'm going to jump to, I don't want to go into this one for now. Okay, so we're going to end on this one. So overall, as you're working with these different solutions, what I wanted you guys is to get a feel for what does Cadence have. I wanted you to get a feel for what is out there as far as design and implementation, right? What's the flow look like, right? Where do I start from? Where do I start? Where do I end up? Okay. What do I need to start thinking about when I'm going into physical implementation, when I'm going into RTL synthesis, when I'm going into HLS, right? So I know that these didn't give you the detailed trainings. I have a ton of detailed trainings online and available to you, and it's self-paced, and you can go that. I believe you guys have a support.cadence.com account you can access, and you can go through those trainings. You can certify on these trainings too, by the way. So you can put these certifications on your resume. That's something very useful to do, right? All the HLS trainings on there too, right? When you go from beginning, intermediate, or advanced, if you want to go learn it, it's there, okay? So that's why I didn't dive into those things and switches and options, because we would be here for another 2 days to do that, okay? So we're not going to do that. But I did want you to give us a high-level sense of what's out there, how this all integrates, and how it applies to you. All right, thank you guys.